Hello viewers, in this video lecture, today we are going to talk about the massive open online course on emerging technologies in renewable energy sources. Name of the module is Energy Audit Fundamentals, in which I am going to discuss about lecture 4, Motor and its efficiency. In the last video, we have learnt about energy audit survey items. So, viewers, here are the important topics which will be discussed in this video. First is introduction of motor, types of motor, application of motor, key points in magnetic field theory, induction motor, working of induction motor, types of induction motor, losses in induction motors, motor efficiency. Now, let us discuss in details. Motor. A motor is a device that converts electrical energy into mechanical energy, producing motion or rotational movement. It is a fundamental component in various machines and devices used in everyday life and industrial applications. Motors are crucial for driving mechanical systems, automation and transportation. The basic principle behind the operation of a motor involves the integration of magnetic fields generated by electrical currents. When an electric current passed through a conductor placed within a magnetic field, a force is exerted on the conductor, causing it to move. By arranging conductors and magnetic fields in specific configuration, motors can generate continuous motion. Now, let us discuss about types of motor. There are several types of motors, each designed for specific applications based on their operational principles and characteristics. Here are some of the various types of motors. First, direct current motors, also abbreviated as DC motors. DC brushed motors. These motors have a rotating armature and use brushes and a commutator to switch the current direction, causing the armature to rotate. There are simple and widely used applications like toys, small appliances and automotive systems. DC brushless motors, also abbreviated as BLDC, also known as electronically commutated motors. They do not have brushes or a commutator. Instead, they use electronic controllers to switch the current in the windings, making them more efficient, reliable and suitable for the applications like electric vehicles, computer cooling fans and industrial equipment. Second is AC motors, that is alternating current motors. Induction motors, there are the most common type of AC motors and work based on electromagnetic induction. They have a fixed stator and a rotating rotor. Induction motors are widely used in industrial and commercial applications such as pumps, fans and conveyor systems. Synchronized motors. Synchronized motors rotate at constant speed that synchronizes with the frequency of the AC power supply. They are used in applications where precise speed control is required, such as in clocks, record players and industrial machines. Single phase motors. These motors are designed to run on single phase AC power and are used in smaller applications like washing machines, compressors and small fans. Three phase motors. Three phase AC motors are more efficient and powerful than single phase motors, making them suitable for heavy duty industrial applications such as compressor, pumps and industrial machinery. Other different types of motors. First is stepper motor. Stepper motors move in discrete steps when electrical pulses are applied to their windings. They offer precise control over motion and position, making them ideal for applications like 3D printers, CNC machines and robotics. Second is servo motors. Servo motors are the type of closed loop system with feedback control. Third is linear motors. Unlike traditionally rotary motors, linear motors produce motions in a straight line. They find applications in high speed transportation systems, magnetic levitation, trains and some CNC machines. Fourth, universal motors. Universal motors can operate on both AC and DC power sources. They are commonly used in household appliances like vacuum cleaners, blenders and power tools. Fifth is hermetic motors. Hermetic motors are designed for sealing against the outside environment. They are commonly used in refrigeration, compressors and air conditioning systems. Sixth, hysteresis motors. These motors use the principle of hysteresis to create rotation. They are used in clocks, record players and other precise applications. Each type of motor has its advantages and disadvantages, and the choice of motor depends on the specific requirement of the applications such as speed, torque, efficiency and cost. Application of motors. Motors have a wide range of applications in various industries and everyday life. They are used wherever mechanical motion or rotational movement is required. Here are some common applications of motors: industrial machinery, HVAC systems, home appliances, automotive industry, aerospace and aviation, robotics, power tools, pumps and fans, electric generators, marine applications, medical devices, entertainment, space exploration. These examples demonstrate the versatility and importance of motors in modern society. They are integral components of countless devices and systems that improve efficiency, automate processes and enhance our daily lives. As technology advances, motors continue to play a significant role in shaping various industries and driving innovation in numerous applications. The key points in magnetic field theory. Magnetic field theory is a fundamental concept in physics and plays a crucial role in understanding the behavior of magnets, electromagnetic phenomena and various devices like motors, generators and transformers. Here are some key points to understand about magnetic field theory. Magnetic fields and magnetic flux. A magnetic field is a region in space where magnetic forces are exerted on magnetic materials or moved charged particles. Magnetic fields are typically represented by lines of force called magnetic field lines. The quantity of magnetic field passing through a surface is known as magnetic flux. Second, magnetic poles. All magnets have two poles, a north pole and a south pole. Unlike electric charges, magnetic poles cannot exist independently. They always come in pairs. Third, magnetic dipole. A magnetic dipole is a magnetic object or system that has two magnetic poles of equal strength but opposite polarity separated by a small distance. fourth is magnetic field strength. The magnetic field strength at a point is the magnetic field produced by electric currents or magnetic materials at that location. It is measured in amperes per meter. Fifth is magnetic flux density. The magnetic flux density at a point is a measure of the strength of the magnetic field in a given region. It depends on both the magnetic field strength and the magnetic properties of the material in the region. It is measured in Tesla or Gauss. Sixth is permeability. Permeability is a material property that relates magnetic flux density to magnetic field strength in a magnetic medium. It is a measure of how easily a material can be magnetized and is expressed in Henries per meter. Magnetic induction versus magnetic field. Now, let us discuss about it. Magnetic induction includes the effects of both free currents and magnetization currents in a magnetic material, while magnetic field only accounts for the free currents. Eighth, magnetic materials. Let us discuss this in detail. Materials can be classified into paramagnetic, diamagnetic and ferromagnetic based on their responses to magnetic fields. Ampere's circumstantial law. Ampere's law relates the magnetic field around a closed loop to the electric current passing through the loop. 10th is Faraday's law. Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction states that a changing magnetic field induces an electromotive forces EMF or voltage in a closed loop. Next, that is 11th point, is Lorentz force law. This Lorentz force law describes the force experienced by a charged particle moving in a magnetic field. 12th, magnetic flux and Gauss law. Gauss's law for magnetism states that the net magnetic flux through any closed surface is 0. Now, let us discuss about magnetic field theory. Magnetic field theory is essential for understanding the behavior of magnets, the principles of electromagnetism and the operation of various electromagnetic devices in the physics and engineering. It provides the foundation for many applications in modern technology and industry. Now, let us discuss a bit about induction motors. An induction motor is an AC, that is alternating current electric motor, in which the electric current in the rotor needs to produce torque is obtained by electromagnetic induction from the magnetic field of the stator winding. An induction motor can therefore be made without electrical connections to the rotor. Next, we will discuss about applications of induction motor. Induction motors are widely used in a variety of applications such as industrial pumps and compressors, fans and blowers, conveyor systems, machine tools, household appliances like washing machines, refrigerators, etc. It is also used in heating ventilation and air conditioning systems. It is also used in water treatment plants. It has wide application in the field of power generation. It is also called induction generators. Now, working of induction motors. The working principle of an induction motor is based on The phenomena of electromagnetic induction. It is a type of alternating current, that is AC motor, which means it operates on an AC power supply. Induction motors are widely used in various industries and commercial applications due to their robustness, simplicity and efficiency. And induction motor consists of two main components, the stator and the rotor. Let us understand about what is stator. The stator is a stationary part of the motor and consists of a laminated steel core with evenly spaced slots. Copper or aluminum windings are placed in these slots, which are connected to from three-phase windings. When a three-phase AC voltage is applied to a stator windings, a rotating magnetic field is created in the air gap between the stator and rotor. Now, let us understand what is rotor. The rotor is a rotating part of the motor and is usually made of a cylindrical laminated steel core with evenly spaced slots. The rotor can be of two types. Wound rotor. This type has a rotor winding connected to slip rings, allowing external control of the rotor resistance and speed. Wound rotor motors offer additional control capabilities but are less common. When the three-phase AC supply is connected to a stator windings, it creates a rotating magnetic field that continuously change direction with the alternating current. This rotating magnetic field induces currents in the rotor according to the Faraday's law of electromagnetic induction. The induced currents in the rotor create their own magnetic field which interacts with the rotating magnetic field of the stator. The interaction between the rotating magnetic field of the stator and the induced magnetic field of the rotor causes a torque to be generated, propelling the rotor to rotate. The rotor rotates at a speed slightly lower than the speed of a rotating magnetic field, a phenomena known as slip. The difference between the synchronized speed of rotating magnetic field and the rotor speed is called slip. The speed at which the rotor rotates depend on the slip and the frequency of the AC supply. Induction motor operate at almost constant speed, that is synchronous minus slip, under varying loads, making them suitable for a wide range of applications including pumps, fans, compressors, conveyors and many more. The simplicity, reliability and efficiency of induction motors have made them the workhorse of many industrial processes and systems. Next, we will study about types of induction motor. Induction motors are a type of AC, that is alternating current motors, that operates based on electromagnetic induction. There are two main types of induction motors based on their design. First is squirrel, that is cage induction motors. Squirrel cage induction motors are the most common type of induction motor. They have simple and robust rotor design, making them reliable and cost effective. The rotor consists of a cylindrical core made of stacked laminations. Copper or aluminum bars are placed in the slots on the rotor core and the ends of the bars are short circulated by end rings resembling a squirrel cage, hence the name called squirrel cage. Next is wound rotor induction motors. Wound rotor induction motors, also known as slip ring induction motors, have a more complex rotor design compared to squirrel cage motors. The rotor windings are not short circulated like in squirrel cage motors. Instead, the rotor windings are connected to external resistors or slip rings. The slip rings allow external electrical connections to the rotor windings. Both types of induction motors are widely used across industries due to their efficiency, reliability and versatility. The choice between squirrel cage and wound rotor induction motors depend on specific application requirements such as speed control, stating torque and cost consideration. Now let us discuss about the losses in induction motors. Induction motors offer several advantages including simple construction, low maintenance, high reliability and the ability to run on alternating current power grids, which are prevalent in most countries. However, they have limitations regarding speed control compared to some other motor types like DC motors and servo motors. Despite this limitation, induction motors remain an essential workhorse in many industrial and domestic applications. Induction motors, like any other electrical machines, experience various losses during their operations. These losses impact the motor's efficiency and overall performance. The main losses in an induction motor includes: first, copper loss, that is I square R loss. This loss occurs in the stator at rotor windings due to the resistance of the conductors. When a current flows through the windings, some of the electrical energy is converted into heat due to the resistance of the copper wires. Copper losses are proportional to the square of the current, that is I square, and are predominant at full load. Second is iron loss, also called core loss. Induction motors have a laminated steel core in the stator and rotor to reduce eddy current losses. However, there are still some losses due to high stresses and eddy currents within the core materials. These losses are present regardless of the load and contribute to the motor's no load losses. Third we have is mechanical losses. Mechanical losses occur due to friction and winding within the motor. Friction losses include bearing friction and losses in mechanical couplings, while windage losses are caused by air resistance to rotating parts. These losses are dependent on the motor speed and load. Fourth is stator iron loss, that is stator core loss. This loss specifically refers to the iron losses in the stator core. The main losses include copper losses, that is I square R losses. Second is iron losses, that is core loss. Third is mechanical losses. Fourth is stator iron loss. Fifth is rotor windage loss. Sixth is stray load losses. Seventh is stator and rotor leakage. Eighth is load dependent losses. It is essential to minimize these losses to improve the motor's overall efficiency. Now, reduction of losses in induction motor. This can be reduced by selecting high efficiency motors. Second, by selecting proper sizing and matching. Third, by selecting voltage regulation. Fourth, by the use of variable frequency drives. Fifth, by efficient motor controls. Sixth, by efficient bearing and lubrication. Seventh is premium insulation materials. Eighth, efficient cooling. Ninth is optimized stator and rotor designs. 10th is by efficient lamination. 11th is regular maintenance. Now let us discuss a bit about motor efficiency. Motor efficiency refers to the ratio of mechanical output power to the electrical input power in an electric motor. Higher motor efficiency indicates that lesser energy is wasted as heat or other losses, making the motor more economical and environmental friendly. Efficient motors are essential for minimizing energy consumption and reducing greenhouse gas emissions. Types of motor efficiency. Motor efficiency can be categorized into different types based on how it is measured or defined. Here are some common type of motor efficiencies like first, nominal efficiency, second, peak efficiency, third, full load efficiency, fourth is part load efficiency, fifth, service efficiency, sixth, energy efficiency index, seventh, annual energy efficiency, eighth, annual energy efficiency.